All right, next up is question 3, and part A says to sketch the solid whose volume is given by the iterated integral here, and our integrand is r, and the order of integration is dz d theta dr. And just to clarify here, when it says sketch the solid whose volume is given by this iterated integral, well, if I look at this r dz d theta dr portion here of the integral, this is really just our differential volume element in cylindrical coordinates. So this iterated integral here is equal to the triple integral over some solid E, whose graph we're about to sketch, of just dV, and that, of course, is the volume of our solid E. Okay, so let's go ahead now and sketch the solid. So to start, let's look at the bounds for z. Z ranges from r up to 2. And now, as we saw back in problem 1 on the worksheet, z equals r is equivalent to z is the square root of x squared plus y squared. So this is just describing a right circular cone that runs along the positive z-axis. Now z equals 2, this is just the plane parallel to the xy plane, just shifted up 2 units along the z-axis. So if I put in our cone, z equals r, and our plane, z equals 2, we're saying that for a fixed theta and r, we're going to let z vary from the cone up to the plane. So here z is r, and here z is 2. Okay, so now for theta and r, well, we're letting theta vary from 0 to pi over 2, so that's going to restrict us here in the first quadrant. And then letting r vary from 0 to 2 tells us that, in fact, we're just going to be integrating over a quarter disk here in the first quadrant down here in the xy plane. Okay, so in fact, we're looking at this solid quarter cone for our region E. So it's just the portion of the solid cone that lies in the first octant. Okay, now of course we could actually compute this volume really simply just because it's a cone, but the problem doesn't ask for that, so we'll just stop there. Okay, great. So now let's go ahead and look at part B. And so this is asking us to compute this iterated integral here. And again, let's start by sketching the domain of integration. And so z is varying from the xy plane, right, at 0, and then up here at the plane z equals 2. And then for x and y, well, we're letting y vary next from 0 to the square root of 9 minus x squared. And that's just the top half of the circle of radius 3 centered at the origin. And then letting x vary from minus 3 to 3 is telling us that we're actually going to cover a half disk there of radius 3. We're going to be covering this half disk, right? So for a fixed x, if we let y vary from 0 up to the square root of 9 minus x squared, this is just going to describe one of these vertical strips. And then letting x vary from minus 3 to 3 is just going to stack these vertical strips to fill out this half disk. And the description of the half disk in polar is nice and simple. Okay, so now let's go ahead and look at the solid we're integrating over, right? So here is our half disk down here in the xy plane, and then we're just letting z vary from 0 up to 2 right here. Okay, and so we're going to fill out this solid you see right there. All right, so now let's go ahead and set this integral up in cylindrical coordinates. So I'm going to let z, well, that's varying from 0 to 2, and right, in cylindrical, z is just playing its usual role, so that is just left alone. And then y and x here, we're going to convert to polar. Okay, and so for that, we're going to let r now vary from 0 to 3, and then we're going to let theta vary from 0 to pi, and do not forget that factor of r that comes from the area element in polar. And then downstairs I have 1 plus, and x squared plus y squared in cylindrical is just r squared. And so this is our integral now in cylindrical coordinates. Great. All right, so let's go ahead and compute. Looking at the integral from 0 to pi, then 0 to 3. And for the z integral, since the integrand r over 1 plus r squared is independent of z, I'm just going to pick up a z and then evaluate that from 0 to 2, and that's just going to give us a 2. So I have 2r dr d theta over 1 plus r squared. And then since this integral here with respect to r is independent of theta, I can go ahead and do the simplifying step by just separating this out. So I have this now, and the integral from 0 to pi of just d theta, that's pi. And here for this integral, well, since I have a 2r dr upstairs and a 1 plus r squared downstairs, that suggests making a substitution where I'm going to let u equal 1 plus r squared. So then du would just be 2r dr. And so we're going to be looking at the integral from, well, if r is 0, u would be 1, and if r were 3, we'd get 1 plus 9 would be 10. Of 2r dr, that's just du over 1 plus r squared, which is u. And this is a logarithm. Okay, so we're going to get the log of the absolute value of u, and then evaluate that from 1 to 10. Plug in 10, we're going to get just log 10. And if I plug in 1, I'll get the log of 1, which is 0. So here is the value of my integral. And that's going to do it. Thanks.